Some of you might not be done yet, but let's go ahead and give these a start. So number one up here, we have the parentheses. So we're going to go left to right. So this is where we start. Where's its other end? Right there? Okay, so in there, what do we have to do first? We've got another parentheses, more enclosing symbols. So we're going to work in there. In there, what do we have to do first? The division. 24 divided by 4, which is, careful, 6. There we go. Okay, so now here we're still working inside that inner set of parentheses. What do we have to do next? Just left to right, it's all addition and subtraction. So 8 minus 6 is 2. I'm going to cheat and just erase them and replace them with a 2. And then 2 plus 3 is 5. Now we've reduced that parentheses to a single number. I can get rid of the parentheses. Do I have to put in any multiplication? No, there was an operation on both sides of the parentheses, so I don't need to do that. So now I'm back out. So I erased my other set here. To my bigger set of parentheses. What did I do wrong? I had it wrong. This was just, what was it? That was just 2 in here. The 3 was outside. There we go. So I can take rid of the parentheses. That's plus 2 in there. That look better? Okay. So now, yes, we got to do the 7 minus 2 inside here, which is 5. And 5 plus 3, which is 8. So now that set of parentheses is down to a single number. I can get rid of them. But this time I have to remember to put in multiplication. It was 2 times the parentheses. So now we're on to that end set of parentheses. What do we have to do first in there? Multiplication. Good. 5 times 2 is 10. And then, of course, 2 plus 10 is 12. Those parentheses are down to a single number, so we can get rid of them. And there is subtraction in front of them, so we're good there. What's next? 2 times 8, which is 16. And then we're just going to add and subtract left to right. 14 plus 16 is 30. 30 minus 12 is 18. Just like I had warned you last week, one of the biggest mistakes is rewriting them. You see, I got caught rewriting it incorrectly there. So, number 2, that fraction bar, remember, tells us we have to do everything on top first, then everything on bottom, and then we can divide. So let's do the top of that first. 7 plus 15 times 3. What are we going to do first? Multiply. 15 times 3 is 45. 7 plus 45, 52. So the top of that is 52. On bottom, what do we have to do first down there? Okay, which one? Left to right. So 5 plus 9 is, or 5 times 9, 45. Next. 7 times 6 is 42. And then 45 minus 42 is 3, and 3 plus 1 is 4. So the bottom is 4. Now what? We divide. 52 divided by 4 is 13. Good. Show of hands on those first two. How many got both of them right? I guess I should put my hand down because I screwed up the first one. That's not too bad. Okay. The next two are dealing with the integers, the negatives. And I did subtraction and multiplication, just because multiplication and division are very similar, and subtraction is going to become addition anyway. So for number 3 here, what did you get? Positive 17. Anybody get anything different? Yeah, that's going to become, the negative 17 doesn't change. Remember, the operation always operates on the number that comes after it. So subtracting a negative 34 is the same as adding a positive 34. We've got negative 17, positive 34. We end up at positive 17. For number 4, negative 9 times a negative 8. First of all, is my answer going to be positive or negative? It will be positive. A negative times a negative is always positive. When we're multiplying or dividing, if we're multiplying or dividing two numbers with the same sign, the result is positive. What is 9 times 8? 72. So negative 9 times negative 8 is just 72. Any questions on those? Okay. Well, we go over those again for a good reason, because today we're going to look at some things that subtraction, especially with the integers, comes into play and is the main source of mistakes in some of the problems we're going to look at today. So what we're going to look at today is we're going to start looking at variables and how they're used. The mysterious letter X. First of all, we mentioned last week that whenever we see these things, there's always a count and a name. Whenever we see an X written all by itself there's something left out. Just like if you take a measurement, you have something that's an inch long, you might just say an inch. It's really implying that is 1 inch long. The same here, if we just say X, it's really implying 1x. So there's one of them, and the name is the X. And the way they work with everything else when we do our operations is exactly like any other number. But before we get into those, I want to talk about some of the uses for an X. First thing that the variable can be used for is for a rule or a definition. And the best example of this is something we mentioned briefly a couple of times last week, but we didn't go into detail just because it's not, I don't like to get that formal. Like properties, you have something called commutative property. We mentioned the commutative property. If we add two numbers, it doesn't matter what order we put them in. So for a commutative property of addition, you might say A plus B is equal to B plus A. All that's saying is when you add two numbers, it doesn't matter what order they are when you add them. For multiplication, same thing. We can write it as A times B equals B times A. We can use a variable to define a rule. Here we had to use a couple of different variables. We can use multiple variables. Associative property. When you have three or more that are added or subtracted, or added or multiplied, I should say. It doesn't matter whether we add the first two and then add the third one to that total, or we can add the last two and then add the first one to that total. We're going to get the same result. And of course, it's the same for multiplication. So we can use a variable, like I said, to define rules like that. The second application of a variable is as a missing value in an equation. For the rules up here, A could be any number. So it could be, B could be any number. Whatever number we need it to be, it can be that. Well, this down here, when it's a missing value in an equation, like 3x plus 7 equals 25. Here, x has a value. We just don't know it yet. We need to figure it out. So we need to find the value yet. So there's a case, it's a missing value in that equation that we have to figure out, that we can find, but it only has one value in that case. The third value, which is going to be the one we're going to work with first, we're going to come back and we will spend quite a bit of time this semester dealing with that missing value in an equation, solving equations. But for right now, we're going to take some time to deal with just a generic value. So we looked at before things like 4x plus 7x. If you recall from our first couple of days, when you add or subtract numbers, first thing is we must have the same name. Do those both have the same name? Yes, they do. They're both x's. Now we're always going to combine the counts when we add or subtract. We keep the same name. So here we combine the counts. 4 plus 7 makes 11, and we keep that name of x. So if we had 5x plus 2y, what are we going to end up with? Careful. We must have the same name. We cannot combine those with addition or with subtraction for that matter. So 5x plus 2y stays just 5x and 2y, or 5x plus 2y. Now that doesn't mean if they're not all the same variable or all the same name that we can't do some combining. We might have 4x plus 7y plus 9x plus 8y. We can still combine here the things that are alike. It would be just like having 4 inches and 7 pounds and 9 inches and 8 pounds. Over here, we can combine the things that are the same. We can combine inches and inches, and we can combine pounds and pounds. Well, over here, it'll be the same thing. The 4x can be combined with 9x. That'll make what? 13x. Yes, we just keep the same name. 7y then, of course, can combine with 8y to give us 15y. Now, there's something awkward about the way I have that answer written. There's actually something missing from it. What is it? We need to have an addition symbol in there, a plus symbol in there. 13x plus 15y. There has to be something that links those together. Since the 15y is positive, we put a plus there. The symbol in front of each of these terms, just like with the operation, the plus here goes with the value that comes after it. So that symbol in front of it can be thought of as an addition or a subtraction. It can also be thought of as an indication of positive or negative. So here, the first one's positive. Each of these others are preceded by a plus, so they are all positive as well. We can have 8x minus 5y minus 3x plus 2y. So here we have the 8x. This is now a negative 3x. So we go to combine 8 and negative 3, make 5x. Good. Now I get asked all the time, well, why can't we just think of that as 8x minus 3x? We can. That would work out. But there are some spots where it gets a little tricky to figure that out. Just think of it as an 8x and a negative 3x being combined. We're thinking of those vectors, 8x and negative 3x. Now we have negative 5y and positive 2y makes a negative 3y. So that's a negative 3. That negative becomes a subtraction that hooks those two together. Now, I'm not going to spend a lot of time dealing with combining those single digits like that. I want to talk a little bit now about multiple digit algebraic numbers. We defined our place values for whole numbers. I can stop there. Anyway, the ones, I'm just writing down as numbers, tens, hundreds, 1,000s, 10,000s, and so on. I'm going to cut it off there. What those values really stand for, and we haven't really talked much about powers yet, exponents. But what those are is those are actually exponents. We have what's called a base 10 number system. What that means is each of these values, each of these place values, is a power, an exponent with a base of 10. 10 to the power of 0 is 1. 10 to the power of 1 is 10. 10 to the power of 2, or 10 times 10 is 100. 10 to the power of 3 is 1,000. 10 to the power of 4 is 10,000. It keeps going like that. Our place values are powers of 10. So if I have a number like 357, that can actually be thought of as, instead of 300s and 5 10s and 7 1s, I can just write it out as 3 times 10 to the second plus 5 times 10. We usually don't write the 10 to the first. We just write the 10 because we don't need the power of 1 on there. Plus 7. Now 10 to the 0 is 1, so we can just leave it as 7. Now when we write it out like that, it looks very similar to an algebraic number like that. 3x squared plus 5x plus 7. This algebraic number is just a number where the bases of the digits are not given as powers of 10. They are x. This is the x squared digit, obviously. This is the x, or the x to the 1 digit. X to the 0 is still just 1. So that last digit is the 1's digit, or the x to the 0 digit. The reason I'm showing you this is these algebraic numbers like this are going to behave exactly the same as these whole numbers did, with a couple of exceptions. The first exception, well, is just the notation here. Our whole numbers we usually abbreviate without the place values written out. Algebraic numbers, we always have to write them out in long form because the place values have to be written out in there. The reason for that comes to our second difference between them. In our whole numbers, we can only have one digit in each place value. In algebraic numbers, we can have 7x squared plus 19x plus 43. We can have multiple digits in each place value. It doesn't matter. The third major difference with a whole number or integer, either every digit is positive or every digit is negative. If I make this a negative 239, well, that's a negative 2 hundreds and a negative 3 tens and a negative 9 ones. In an algebraic number, each digit is free to be positive or negative on its own. I can have 3x squared minus 7x plus 2. So you can see only that middle digit is negative. The first and the third digit are positives. This one's negative. Those are both positive. But with those differences included, it still follows all the same processes. So we'll go over those in a bit. So now we've looked at adding those single digit numbers, adding and subtracting the single digit numbers. How about multiplying and dividing with our single digit numbers? You know, 7x times 3x. Remember when we multiply or divide, first thing is we do not need the same name. So even though these two do have the same name, they're both x's, they wouldn't have to. And we still combine the counts, but when we multiply or divide, we also combine the names. So to do this, it's going to be 7 times 3 is 21. But we also combine the names. X times x is x squared. If we had 5x times 8y, we do not need the same name. So I can combine those. 5 times 8 is 40. X times y is just xy. To divide, 42x divided by 6. Now I could write that out as this too. 42x divided by 6 means the same thing. When I divide, I do not need the same name. So it doesn't matter that it's 42x and then it's just 6 or 6 ones. I'm going to combine the counts. What is 42 divided by 6? 7. There's nothing to divide the x, so that's still an x. There we go. I might have 24x divided by 8x. Here they do have the same names, even though they don't have to. We'll combine the counts. What is 24 divided by 8? 3. And x divided by x cancels out, so it's just 3. Think of it this way. This would be saying if we have a piece that's 24 inches long and we need to cut out pieces that are 8 inches, how many pieces can we get out of it? We can get 3 pieces. The units, the measurement, the inches cancel out. So the x's cancel out as well. We've done squared, so I can throw that in here. We might have 35x squared divided by 7x. 35 divided by 7 is 5, yep. But then we also combine the names. X squared divided by x is x. Remember, we talked a little bit with the negatives about that multiplication. X squared divided by x is asking what number times x equals x squared? Well, that would have to be x. Okay, let's look at some more complex problems then with multiple digit numbers. We're going to go back to the addition. I'm using parentheses here not to make us do something first, but just to separate that part of the problem out. Just like with our negatives, we separated out part of the problem. So I've got 3x squared plus 7x plus 2. Over here, I am going to have 5x squared plus 8x plus 9. Adding these two numbers, like I said, those place values work exactly like our whole number place values. So our addition is going to work exactly like our whole number addition. So I write out the first number, 3x squared plus 7x plus 2. And then I'm going to write the second number underneath it, and I'm going to make sure I line up the place values. So the 5x squared goes under the 3x squared. The 8x goes under the 7x. The 9 ones goes under the 2 ones. And we are adding down these columns. So we can go left to right or right to left here. We're used to going right to left, so let's do that. What is 2 plus 9? It's 11. Now it's positive, so I'm going to put a plus in front of it. What is 7x plus 8x? 15x. Again, that's positive, so I'm going to put a plus in front of it. 3x squared plus 5x squared? 8x squared. And that's it. That's all there is to it, to adding those algebraic numbers or polynomials. Unfortunately, as we said, in an algebraic number, each digit can be positive or negative on its own. So it can become a little bit more confusing when we throw in the negatives. So 7x squared minus 12x plus 8 plus a negative 3x squared plus 8x minus 13. So again, we're going to go ahead and write these out one above the other. 7x squared minus 12x plus 8, negative 3x squared plus 8x minus 13, and we are adding those. So again, we'll work our way right to left. What is 8 plus a negative 13? Ends up being what? A negative 5. So we already have the minus there, so we're good. So it's minus 5. Negative 12x plus 8x. Well, what's negative 12 plus 8? Negative 4, so that'll be negative 4x. And 7x squared plus negative 3x squared. 7 plus negative 3 is 4, so 4x squared. And that's what it comes out to be. So the key is just treating them like whole numbers and then dealing with the negatives. Now, many of you were probably taught, if you had algebra in high school, to just get rid of the parentheses and combine like terms. Well, that's exactly what we did here. This is actually even a little bit more organized than that. We're actually adding them as real numbers. If that's the way you were taught to do it, is take out the parentheses, combine like terms, you like that and it works for you, please feel free to keep doing it. We're going to have you guys try one. Eight x squared plus 13x minus 9 plus 3x squared minus 8x plus 2. Try that one in your notes, and we'll discuss that in just a minute. So we set it up vertically here. Again, if you were taught to drop the parentheses and combine, you should end up with the same answer. Negative 9 and 2 make negative 7. Good. 13x and negative 8x. 5x, so we're going to put a plus in front of it since it's positive. 8x squared and 3x squared. 11x squared. Perfect. So enough with addition. Let's look at the tough part, which is subtraction. So let's look at 8x squared plus 7x plus 12 minus 5x squared plus 9x plus 3. Well, just like what we did with addition, we're going to line this up. Now we are subtracting down each place value, down each column. So starting at the end over here, 12 minus 3 is 12 minus 3 is 9. It's positive, so it's a plus. Now here's where it comes into effect. With whole numbers, we would have to borrow. We can't borrow with algebraic numbers, but we are allowed to have negatives within a single digit. So 7x minus 9x is negative 2x. Good. And 8x squared minus 5x squared? 3x squared. Good. Now the subtraction gets complicated. Now again, many of you were probably taught you change the sign of every number in the parentheses and then take out the parentheses and add like terms again. Same type of thing, adding the opposite. That's just a shortcut for what we're doing here. When we throw in negatives, it gets to be more complicated. Now we had a negative there as a result, but it was a result of subtracting two positives. When a negative is actually one of our digits in the original numbers, it can be a little more work. So let's say we got 5x squared minus 7x plus 3 minus 7x squared plus 13x minus 8. So again, we're going to write them out. We're going to write them out vertically. 5x squared minus 7x plus 3. We're going to line up the 7x squared under the 5x squared, the 13x under the negative 7x, and the negative 8 under the positive 3. And we are subtracting now. Here's where, like I said, I see a lot of calculation mistakes because of the negatives. I always rewrite the problem off to the side and I work with it. This is 3 minus a negative 8. Remember, we are subtracting. 3 minus a negative 8 becomes 3 plus 8. So this is positive 11. This here, negative 7x minus 13x, again, I'll just work with the numbers. Negative 7 minus 13 is going to become negative 7 plus a negative 13. Well, negative 7 and negative 13 make negative 20, and that is still x. We keep the same name. And finally, 5x squared minus 7x squared is a negative 2x squared. I'm going to have you guys try one here in your notes. 3x squared minus 5x minus 13 minus x squared minus 7x plus 4. So I'll give you a few minutes or a minute or two to try that in your notes, and then we'll go over it in just a second. Okay, so we write these out again, lined up vertically. One thing we notice here is that this is just an x squared. Remember, that's really a 1x squared. So here we've got negative 13 minus 4. Can be changed to a negative 13 plus a negative 4, which is negative 17. Good. Here, this is 5x minus a negative 7x. So 5 minus a negative 7 becomes 5 plus 7, which is positive 12x. Good. 3x squared minus 1x squared. 3 minus 1 is 2, so 2x squared. How many of you had that one correct? Okay. How many of you that missed it was because of the negatives? Now, there's a little quirk that happens here. If we go back to whole numbers, if I had 508, if I were writing that out in full form, I would write 500s and 8 ones. I wouldn't bother writing the 0 tens in there because it doesn't add any value to the number. The same analogy exists in our algebraic numbers. We can have 5x squared plus 7, where the x digit is missing. Where that can be confusing is if it's 5x squared plus 7 minus 3x squared minus 4x plus 11. To do this subtraction, we have to have all the digits there. So 5x squared plus 7, we're going to have to fill in 5x squared plus 0x plus 7. So that all those place values are accounted for. Now the 3x squared goes under the 5x squared. Negative 4x goes under the 0x that we put in there. And the positive 11 goes under the 7 ones. And we are still subtracting. 7 minus 11 is negative 4. 0 minus a negative 4 is 0 plus 4, which is positive 4x. And 5x squared minus 3x squared is 8x squared. Any questions so far? Before we can move on then to the next part, we have to discuss exponents a little more. You know, we know that x to the 5th means 5 x's multiplied together. So because of that, what if I have x to the 5th times x to the third. Well, x to the fifth is 5x's multiplied together. X to the third is 3x's multiplied together. If I multiply them all together, I have 1, 2, 3, 4, 5, 6, 7, 8 x's multiplied together. Becomes x to the 8th. The shortcut that you may have learned is when you're multiplying exponents with the same base. They both have to have a base of x here. When you're multiplying exponents with the same base, you can just add the powers. 5 plus 3 gives us 8. So if I have y to the 9th times y to the 15th, what's that going to become? Y to the 24. Very good. 9 plus 15 is 24. If I have, come on, z to the 8th times x to the 4th, what's it going to become? Well, they have different bases, don't they? Z and x. I cannot combine the powers. I can multiply them still, but I can't combine the powers. I can only combine the powers if they have the same base, y and y, or up here, x and x. Since that's a z and an x, I can't combine their powers. So that's just going to be z to the 8th times x to the 4th. Now, a little side note about math grammar. In math grammar, we like to list our variables alphabetically. So we would normally rearrange that as x to the 4th. We drop the multiplication, just do x to the 4th, z to the 8th. That means x to the 4th times z to the 8th, but we don't need the multiplication symbol in there. Okay, it is time for our break here. Let's go now. Well, the good thing it's time for our break because Word just crapped out on me. Okay, so we can combine those powers. X to the 8th times x to the 23rd gives us x to the 31st. Good. 8 plus 23 is 31. Similarly, we can have x to the 5th divided by x to the 3rd. X to the 5th is still 5x's multiplied together. X to the 3rd is 3x's multiplied together. And we can cancel them out. We end up with x squared. So the shortcut for dividing exponents with the same bases is we take the powers and we subtract. 5 minus 3 is 2. So x to the 5th divided by x to the 3rd is x to the 2nd. So if I add y to the 18th divided by y to the 11th, I'm going to get y to the 7th. Good. 18 minus 11 is 7. And again, they have to be the same base. What if I take x to the 3rd to the power of 4? That's saying I have 4x to the 3rds multiplied together. Well, x to the 3rd is 3x's multiplied together. Let me write that a little bit bigger. So if I'm multiplying those all together, how many total do I have multiplied together? Well, there's 12. That's x to the 12. Good. The shortcut when we're taking an exponent to another power is we multiply the powers. 3 times 4 is 12. So if we have y to the 7th to the power of 11, we're going to get y to the 7 times 11 is 77. Now, there are a lot of other things with those powers we can do. A couple of them we'll look at. We said we can't combine the powers, at least. We can multiply them. X to the third times y to the fifth is just x to the third y to the fifth. But if we're multiplying that by another number, or another set of variables, let's say we have x to the sixth y, we can combine each variable, each name, separately. So we have apparently it's going to be, so we will have x to the fifth, y to the third times x to the sixth, y. We can multiply the x's. X to the third times x to the sixth. What is 3 plus 6? 9. So we get x to the ninth. Y to the fifth times y. Well, we have to think of this as y to the 1. So y to the fifth times y to the 1 is y to the sixth. Resume. We might have x to the seventh, y to the third times x to the fifth, z squared. To handle that, we're going to combine, again, the like variables. X to the seventh and y to the fifth combine to make x to the 12th. Now, the y and the z, there's no other y's to combine with the y, and there's no other z's to combine with the z. So they're just going to stay as they are. The question is, what order do we put them in? And we mentioned that earlier, alphabetical. So the y to the third goes first, the z squared then goes last. The same works for division. If I have x to the fifth, y to the eighth, and I am dividing by x to the third, y squared, I can divide each separately. X to the fifth divided by x to the third is x squared, good. Y to the eighth divided by y squared, y to the sixth, thank you. Now again, we have to be careful with those powers. We might have x to the eighth, y to the fifth, z to the third divided by x to the fourth, y, z squared. We're going to get x to the fourth. Very good. 8 minus 4 is 4. Y to the fourth again. We think of this as being y to the 1. 5 minus 1 is 4. And z to the 1 or just z. 3 minus 2 is 1. So z to the 1 or just z. What's x to the 0 equal? For that matter, what's 5 to the power of 0 equal? Well, some say just 5. Some say 0. I'm going to put out there 1. So the question that always comes back, why is it 1? Well, if you remember, our definition of powers is where there's going to be that many of that number multiplied together. 5 to the third power means there are 3 5s multiplied together to give us the 125. 5 to the 0, that means there's 0 5s multiplied together. That makes no sense, does it? So this goes back to our negatives and multiplying two negatives where the definition broke down, so we look for a pattern. 5 to the third power is 125. So we're going to keep the same base, which is 5. I'm going to reduce the power by 1. So 5 to the power of 2 is 25. Well, let's see. 5 to the power of 1 is just 5. The pattern here, whenever the power reduces by 1, the result is divided by 5. So if we keep going, 5 to the power of 0, we reduce the power by 1, the result has to divide by 5. Well, what's 5 divided by 5? 1. So 5 to the power of 0 is 1. And we can show the similar pattern for any number. Any number to the power of 0 is 1. So x to the power of 0 would also be 1. Now we can continue with this. What if I go 5 to the power of negative 1? Now that really makes no sense. How can we have negative 1 5s multiplied together? There's less than 0 of them. But the pattern here is we would divide by 5 again. 1 divided by 5 is 1/5. 5 to the negative 2, well, divided by 5 would be 1/25. 5 to the negative 3, dividing by 5 again would be 1 to the 125th. You can see a pattern developing here where the negative power is related to the positive power. 5 to the negative 3 is just 1 over 5 to the positive 3. We're going to work with those a little bit more when we talk about fractions. This concept here of 1 over a number is called a reciprocal. And when we talk about fractions, we'll talk about that a lot. But for now, I just wanted to continue that pattern. Okay, now let's look at more practical, not more practical, but more specific multiplication rather than just focusing on the powers. So we might have 8x to the third y to the 7th times 2x to the 5th y to the 4th. And just like any other numbers, we're going to combine the counts. When we multiply, we combine the counts. 8 times 2 is 16, but then we combine the names. X to the third and x to the 5th make x to the 8th. Good. 3 plus 5 is 8. Y to the 7th and y to the 4th make y to the 11th. Perfect. Division is going to be the same way. We might have 28x to the third y to the 9th divided by 7x y to the 4th. When we divide, just like multiplying, we combine the counts. What's 28 divided by 7? 4. Then we combine the names. X to the third divided by x? X squared. Good. We think of this as 1. X to the 1. 3 minus 1 is 2. Then we have y to the power of 5. Good. 9 minus 4 is 5. Now, everything we've done here so far has had a positive power, and the result, it is possible to be negative. You know, we could have x to the 4th divided by x to the 9th. That's going to give us, what is 4 minus 9? X to the negative 5. Again, we'll work with those more when we start working with fractions. Well, let's step up. We've looked at multiplication and division now with single-digit numbers. Let's make it a little bit more complex. Let's look at something like this. 5x times 3x plus 7. Well, this can be thought of just like having, 4 times 32, where we wrote it like this, 32, 4. I always put the number with the fewest digits on bottom. And I did 4 times 2 is 8. 4 times 3 is 12. This can be done the exact same way. I put the 3x plus 7 on top. Put the 5x on bottom. 5x times 7 is 5 times 7 is 35, and then there's nothing to combine with the x, so it just stays x. That's a positive 35x, so we're going to put a plus in front of it. 5x times 3x is somebody said it there, 15x squared. 5 times 3 is 15. X times x is x squared. Now, many of you have seen problems like this before. And I've heard of a thing called distributing or distribution. All that is a shortcut for this process here, where they take the 5x and they just multiply it through going backwards. 5x times 3x is 15x squared. 5x times 7 is 35x. Now, to me, this makes more sense because it's the same as the way we would multiply our whole numbers. But I realize this is shorter and a little bit quicker. And if that's the way you were taught and you're good at it, please feel free to keep doing it. You should come up, you better come up with the same answer either way. We might have 7x squared times 5x minus 4. It's the same thing, 5x minus 4 times 7x squared. 7x squared times negative 4. What do we get? Perfect, negative 28x squared. 7x squared times 5x. 7 times 5 is 35. X squared times x is x to the third. Good. Any questions? Now again, you could have done the distributing. 7x squared times 5x. 35x to the third. 7x squared times negative 4 is negative 28. X squared. That works just fine. I'm going to have you guys try one. See if you can figure that one out. Excuse me. So, throwing in the third term there looks a little different, but it's the same process. I'm going to go ahead and shorten up and just do the distributing here. 3x times 8x squared is 24x to the third. Great. 3x times negative 9x. Perfect. Negative 27x squared. And 3x times 7? Positive 21x. Any questions? So then our next step, take something like 3x plus 5 times 2x minus 7. This again is just a long multiplication. Write it out as 3x plus 5 times 2x minus 7. As we saw when we did our multiplication with our whole numbers, we start with the last digit of the bottom number, in this case, the negative 7. times the last digit on the top number. Negative 7 times 5 is negative 35. Then we move over to the next digit in the top number. Negative 7 times 3x. Careful, negative 7 times 3x. Negative 7 times 3. Yeah. There we go, negative 21 and then x. Now we're done with the top number. We're going to move over to the next digit on bottom. When we do that, we have to leave a space or put in a 0 down here. 2x times 5 is 10x, so it's positive. We'll put in a plus. 2x times 3x. 6x squared. Good. And now we can combine. We got negative 35 and 0 is just negative 35. Negative 21x and positive 10x is a negative 11x. Then 6x squared. Many of you, if you had algebra before, probably learned a process called FOIL. And this is the way I'll probably do it in front of the class just because it takes up less space. But this really is the process, long multiplication. FOIL is just a shortcut for it. In FOIL, what does the F stand for? First. So you multiply the first digits of each number. 3x times 2x is 6x squared. Just what we had down here. What does the O stand for? Outer or outside. We multiply the outside digits. 3x times negative 7, negative 21x, just like we got here. What does the I in FOIL stand for? Inner or inside. We multiply the inner two digits together. 5 times 2x is positive 10x, again, just like this one here. And finally, the L stood for last. You multiply the last digits of each number. 5 times negative 7 is a negative 35. But you see we've got a negative 21x and a 10x that need to be combined. So 6x squared, we combine those to get a negative 11x minus 35. This is a little bit quicker and takes a little less space, but if you have to, the long way here, to me, makes a little less chance of making mistakes. A little bit easier to do, just a little bit longer. Okay, let's look more at division. You know, we've divided the single digit numbers. I want to move up into multiple digit numbers. If I have something like 648 divided by 2, we start at the left and move to the right. 2 goes into 6 how many times? 3. 2 goes into 4. 2 and 2 goes into 8. 4. Now, there's a very specialized example I gave there because the 2 divided into each digit without any remainder. So we didn't have to go through the whole long division. In fact, we could have done it like this, where it's just 6 divided by 2 is 3, 4 divided by 2 is 2, 8 divided by 2 is 4. So you get 324. That same process, the simplified process, applies to our algebraic numbers. We might have 24x to the 5th minus 16x to the 3rd plus 32x to the 2nd. And we'll be dividing by 4x. Well, just like we did up here where we divided one digit at a time, we're going to do the same down here. We're going to divide one digit at a time. 24x to the 5th divided by 4x. Well, we divide the counts. 24 divided by 4 is 6. X to the 5th divided by x, x to the 4th. Then we move to the next digit. This is a negative 16x to the 3rd divided by 4x. What's negative 16 divided by 4? Negative 4. X to the 3rd divided by x, x squared. Good. And finally, 32x squared divided by 4x. 32 divided by 4. 8. X squared divided by x is just x. We're going to do more examples of this when we get to factoring later on in the course. So I want to move on then to some more complex examples of our multiplication. We can run into things like this. So this is actually coming down to an order of operations problem. It looks more complex, but it's really nothing different than like 3 times 4 minus 2. You have to multiply first. 3 times 4 is 12, and then subtract the 2, which gives you 10. Same thing has to happen here. We have to multiply first. 7x times the 5x minus 3. Now, when I say order of operations, when we think of order of operations, we're used to seeing parentheses and thinking we have to do something there first. Well, here, inside this parentheses, there's nothing that can be done in there. 5x minus 3 cannot be combined in any way. So that is as simple as it can get. In this case, those parentheses are just separating out the 5x minus 3 as a single number. So whenever we see parentheses, there's a second question we should ask. The first one is there anything I should do here inside the parentheses first? In this case, that answer is no. The second question then is there anything that needs to be done, any operations that need to be done to the parentheses? And in this case, there is. It is multiplied by the 7x. Now, as we look through the problem, there's no other order of operations level of priorities. There's no exponents, no other enclosing symbols, no exponents. So we can go ahead and do that multiplication. I'm going to use the distributing method to save some space. 7x times 5x. 35x squared, good. 7x times negative 3. Negative 21x. Now we still have the negative 12x squared here. What more can we combine here? Perfect. 35x squared and negative 12x squared make what? 23x squared minus 21x. Now I get this question all the time as well. How come here we were able to combine x and x and get x squared? Why did we combine powers there? But here, why did we keep it x squared? Well, because up here we were multiplying. And remember, when we multiply, we combine the names, so we combine the powers on the variables. Down here, we were adding or subtracting, and when we add or subtract, we keep the same name. We keep the same power on the variable. I'm going to have you guys try one in your notes here quick. So 7x squared minus 5x, then in parentheses, 3x squared minus 2, 2x, I should say, plus 4x to the third. Give that one a shot. We'll talk about it in just a minute. So looking at this one, the first thing we have to do is the multiplication in the middle here. Now, rather than multiplying this and then treating this as subtraction, it's simpler if we treat this as a negative 5x multiplied through there. So the 7x squared up here is not going to change. That quit on me again. 7x squared is not going to change. Negative 5x times 3x squared is negative 15x to the third. Negative 5x times negative 2x is plus 10x squared. And then we still have the positive 4x to the third at the end. Apologize for the sloppy writing. I have to write with my finger instead of my pen. My pen stopped working again. So anyway, we got things we can combine here. Now we talked about the math grammar going alphabetical when there's more than one variable. If there's more than one power of the variable, we tend to go in something called descending order. What that means is from largest power to smallest power. So we have the third, x to the third first. Negative 15 and positive 4 make negative 11 x to the third. And then we have the 7x squared and the 10x squared make 17x squared. Okay, last thing we want to cover before we call it a night is formulas. Evaluating expressions is the term. Now the command that would be given for what we were doing up here would most likely be simplify. When you see simplify, that's telling you to combine as much as you can. But you may not get it down to a single answer. Like here, we had negative 11x to the third plus 17x squared. We couldn't combine that down to a single term or a single digit. When we say to evaluate expressions, when you're given that command to evaluate, that means your result should be a single number. So when we're asked to evaluate expressions, we might be given something like AB minus D for A equals 3, B equals 7, and D equals 5. So literally evaluate means give value to. So we're going to use these values for the variables. So A becomes 3. Now we know AB implies A times B, so it'll be 3 times. B is going to be 7, and D is going to be 5. So once we have replaced each variable with the numerical value, it simply becomes order of operations. 3 times 5 is, 3 times 7 is 21. 21 minus 5 is 16. We might have 4x squared minus 7y plus z. For x equals 3, y equals 2, and z equals 5. So same thing, we're going to replace each value with its corresponding numerical value. So 4x squared becomes 4 times, what does x squared become? 3 squared, right? Minus 7y is going to be 7 times 2. I got this thing to work here. 7 times 2 plus z is 5. So then I have to do the exponent first. 3 squared is 9. So 4 times 9 minus 7 times 2 plus 5. Then we have to do our exponents, or not exponents, multiplication and division. Left to right, 4 times 9 is 36. We got to do the 7 times 2 is 14. Now I get asked here all the time, why did I treat that as a positive 7 times 2, even though there's a minus in front of it? When up above, when it was 5 times the parentheses, or 5x times the parentheses, why did I treat that as a negative 5x and multiply it through? Well, because when I'm dealing, I could treat this as a negative 7. But what I would have to do is I'd have to make this plus a negative 7. So this would become positive down here. That would be positive instead of subtraction. Now this would be a negative 14. But when I'm dealing with numbers, it's easier to subtract than it is to deal with negative numbers. So that's why I left that as a positive 7 times 2 to get a positive 14. So now it's 36 minus 14 is 22. Had I made that a negative 7, it would be 36 plus a negative 14, which would still be 22. It's just easier for me to think in terms of positives. Then 22 plus 5 is 27. Okay, that's it for new material. I'll let you guys have our last 10 minutes here if you want to get started on homework. I've had a couple people inform me they're having problems getting into my math lab. You'll have to call the Pearson customer service. In fact, I don't think they have a phone number anymore. I think it's a live chat. So when you go to log in, you'll have to click on assistance. So you have a homework that was due tonight. If you didn't get that done, you can still go finish it. The system will just give you a warning that you're going to lose half your points for working on it. Ignore that warning on this first one. We'll make an exception. There is a new quiz. That's quiz 1. That's going to be due tomorrow. That'll be Wednesday at 11:59 p.m. That will absolutely cut you off at 11:59 p.m., by the way. So even if you're not quite, if you're halfway through it, the system will lock you out. And there is a new homework assignment due for Thursday, class time. So if you're having any problems with my math lab, make sure you contact me so I know what's happening, and then contact the live chat with Pearson customer service, see if they can help you get it figured out. Okay, that is it. Like I said, you can have the last 10 minutes here to start on homework or quiz or whatever you want to do. Otherwise, we'll see you on Thursday.